This here is a little interesting thing I saw. Organic compound. Here's the compound down here. Yeah? That nice little organic compound is able to make plants sort of drought tolerant. This is two plants without water. One not given the compound like as a fertilizer or something. Wilting without being given water. This one, no water, still going strong. So some botany type application. Amazing organic compound. Lots of research being done. I thought that was kind of interesting. Okay, top of the hour, let's get started. Good morning to everybody. Any questions about the syllabus? Any questions about the syllabus? Okay, functional groups. Let's see where we left off at yesterday. Any questions about yesterday? I would expect 3/4 of the class to be having questions. Questions?
I have a question about, are we going to go over the gold sheet or do we ask questions about that?
We can look at the gold sheet. The gold sheet has turned into purple though. Well, I noticed a couple of mistakes in the gold and one bit was cut off. Throw away the gold sheet and replace it with the purple. I'm going to try to split these in half each time. Again, if they're run out, make sure everybody gets them. But the first of the gold sheet is good. What was the question on the gold sheet?
Sorry.
Question about the gold sheet?
Oh, so the first one,
Uh-huh.
like, I guess, are you going to give us the answers or do we just need to go through, do we ask you for the answers?
Basically,
I guess
at least we can discuss what type of questions came up. These are sort of focus questions. What kind of questions came up here?
So we did the structures together, but we were just, it has 70 electrons in all the bonding.
70
Standard,
electrons.
or that's what we thought, valence electrons.
Hold on. For what?
The first one?
You mean this formula?
Yes.
7 valence electrons?
70.
Oh, 70.
Doesn't matter.
Okay.
Anyway.
I'm not sure, but more than 7. Okay, go ahead.
We were just curious, like, how do we know if we got the right one? If all of them have standard bonding and the
Well,
right number?
formula that big, you can have many constitutional isomers.
Okay. That's
Yeah.
what
Okay, I mean, yeah, bigger the formula, the more. What'd you get? You got structure? Okay. Okay. One thing will say about this on the functional group page is I probably would not do this sort of systematically like we were doing. That's good for small. Once you get more, a little bit more experience, and I say a note in the functional group page. First off, DUS is most important to me. How many DUS did you come up with?
I didn't calculate it, but
DUS, very important. I would do that because that's going to help you tell you what's in the structure. US. Anybody get a structure for this? Anybody else? Uh-huh.
I got 2.
You got what? I can't hear you.
2 DUS.
2 DUS? Is it 2? Okay. Anybody else? I mean DUS here. Let's do that. We can ignore oxygen. Nitrogen, you add 1. Halogen, you subtract 1. So that's a wash there. So that's all a wash. 8, 2n plus 2 is what? 18? We got 14, so it's missing 4. Yeah, 2 DUS. Okay, 2 DUS. Since it has 2 DUS, really not quite ready to talk about yet. But for example, can it have a benzene ring?
Yes.
Can this compound have a benzene ring?
Yes.
No, because
No.
benzene ring is 4-DUS right there. Okay? If I drew a benzene ring, that would be 4-DUS right there. This compound can only have 2. We can't have a benzene ring. Okay? Basically, keep at it. I'm not quite sure we're ready to answer that one yet. Ester in one, not the other. Really, number 2, I think, would be a little bit more in line with what we can do. I should maybe flip those. Number 2. Okay? Whenever I feel like we have time to look at those, we will. But we do need to keep up a good pace. Let's get going here. I'll make a comment on the functional group page. It's written there. Actually, I think it's written on the outline page. Our outline is green, yeah? Functional groups. We can shorten that to fun groups, yeah? Okay. Somebody asked, the name, it says functional group over here, whatever, type of compound. This is the name we need to know. These are the functional groups. I don't understand how they call it that. This is an aldehyde. This is a ketone. This is a carboxylic acid. Functional groups are on the left side. That's the name. Okay? Sometimes, you know, there's other names that can go along, like a nitrile contains a cyano group. Okay? Please ask. There's a couple of more. So nitrile, sulfonamide. You see these examples of assigning functional groups? By the way, on the first page we did miss. We did skip the benzene ring, I think, didn't we? Benzene ring is the 6-membered ring with 3 pi bonds. It's your classical aromatic compound. An aromatic compound is one in which all atoms in the ring have a p orbital. Once we start doing hybridization in 5 minutes, we'll see that. That's the benzene ring. And you see the benzene ring has how many DUS? 4. Okay, classical. Lots of compounds contain the benzene ring. It's your classical aromatic. Both of these example compounds over here contain benzene rings, okay, or it's a type of aromatic ring. But you see the assignments. Otherwise, did these look right? All these assignments look good. Ether, right? Okay, when the OH bond is bonded to a benzene ring, that is a type of alcohol, but it's more appropriately called a phenol. A phenol. OH on a benzene ring. When you have an NH2 on a benzene ring, it's a type of amine, but it's more appropriately called an aniline. Now, it's got the ing ending. You might call it aniline, but it's pronounced aniline. It's a specific type of amine bonded to the ring. Now, you can put other things on the nitrogen and it will still be an aniline. So in general, it's an aniline. Other things on the ring, it's still a phenol. Okay? So please also know those. For practice, you can identify the functional groups and the drugs on the drug sheet in the syllabus. Yeah? Where's the syllabus? Drug sheet in the syllabus. Allegra, what functional groups do you see? What is this here? Carboxylic acid. What is this here? Alcohol. It contains the hydroxy group. Yeah. What is this? Not an aniline. Why do you call it an aniline? No, only if it's bonded to an aromatic ring, benzene ring. It's not. This is just an amine. What type of amine? Primary, secondary, tertiary. Tertiary amine. Okay. Alcohol. All right. So practice, you can do those. There's also a sheet in the workbook, very similar for practice with the answers given there. That's a very important page. Of course, they're all important, but in the workbook, page Page 2, yeah. All drugs ask you to do different things like DUS, functional groups, hybridization, and the key is given in the back, okay? Some of the same drugs on the syllabus sheet. Anytime you look at a compound, you can say, oh, wow, functional groups are there. What DUS is there? Practice. Ask yourself questions. Okay, green sheet. Let's see. I made a comment there. First off, flashcards. As you noted maybe in the syllabus, flashcards are very good. As a study aid, you can write, draw your functional group on one side, on the flip side have the name. Okay, then just preparing them helps you learn them, but then you have them for practice. So you can use flashcards for other things. Okay, some type of question on the front, or some type of prompt, and then the answer on the back. Okay, and then you use them, and you're like, okay, this, turn it over, and ooh, I forgot that. Okay, so they help you do that. Anybody need any flashcards? Got some somewhere. Anybody need any? Can you catch? You can catch? Composition notebook. I think I may have talked about it in the syllabus, almost like a journal, writing questions. You need one? Okay. Green sheet, functional groups, flashcards. Secret advice. Secret advice. Use your knowledge of functional groups and DUS to help draw a compound from a given formula. Okay? For example, C7H6O2. Okay? C7H6O2, how many DUS does that have?
One.
5. Okay, since it has 5 and it has 6 carbons, boom, I can draw up a benzene ring. Okay, there's 6 carbons right there. I only need one more carbon. I also need one more DUS. So I can put another carbon here, and I also need 2 oxygens. Maybe I can put a carboxylic acid. If you throw an H on there, indeed, that's a formula. And there's your 5 DUS. But I knew I could put together maybe a carboxylic acid because it has 2 O's. And my formula has 2 O's. So I'm using functional groups are your building blocks for your molecules. And if you know them, then you can just build a molecule real quick. No DUS. You can check this. This should have 6 H's, right? 5, 6, yeah. Something like that. So I didn't have to do it 1 carbon at a time and all that systematic. Knowing the systematic is good. You can also do something like that. And as you go along, you'll get a little bit more experience and we'll do those secret advice things. Okay, time to move on to Roman numeral 4, hybridization. Methane. Okay, let's look at methane. By the way, methane. I sent you a handout by email that I expect you to print. It look like this, alkanes, cycloalkanes, yeah? And in there is your nomenclature. Nomenclature of alkanes. That's covered by video only. Okay? With the nomenclature, you'll need to learn your prefixes. Okay? And if you're looking at alkanes, the prefix tells you how many carbons. Meth is 1, F2, Pro 3, But 4. Octane is 8. Everybody knows that, right? Okay. So we say methane, we're talking about a 1-carbon alkane, and it's just CH4. Please be looking at your nomenclature by video. But methane. So we have CH4. Structure. You know, maybe yesterday we just drew this out like this, yeah? It makes 4 bonds. It now has an octet. Each H has a duet. Looks like a good structure. That's why it's CH4 and not like CH5 or CH 2. There we go. But what about the bond angles? And what type of bonds are being used here? Other than just calling them single bonds. You need to look at stuff like that, and that's going to be called your hybridization. Okay? For example, as drawn, this looks like a 90-degree bond angle. Ninth grade geometry, it looks like a right angle. But guess what? It's not. So that's really not a correct drawing. So, what type of orbitals is the carbon using? I'm going to draw, remember ground state? What do we have? A 2s and a 2p. Talk about valence orbitals. Okay, a little close there. What do we have? Ground state looks like this, right? Valence orbitals. What type of bonds? We're looking to fill these, so we need 1, 2, 3, we need 4 electrons to fill all this. That's why it makes 4 bonds. But look, if the extra electrons just came in here, what would you have? You would have the valence, you would have, what is this? That looks like a lone pair. 2 electrons of carbon not bonding to anything. That's like a lone pair. I don't know how you get that. And it looks like you only make 2 bonds. So this is it just doesn't make sense. That's because when most atoms bond, they don't bond in the ground state. I'm not sure what the ground state's useful for other than make it like interesting in chem. Maybe if it's just plain carbon, but even just, I don't know. It's a starting point. Carbon bonds in a hybridized state. What we know is this is 4 identical bonds. We know that because we can study that and determine that. How do you make 4 identical bonds if you don't even have 4 identical orbitals? So that's an s orbital and 3 p's. They're not going to make 4 identical bonds. So, pretend that's not the way there. We're going to hybridize. And usually when I do this, I like to do something like this and say hybridize or mix. Hybridize is just a fancy word for mix. We're going to mix these all up and then we're going to make some new ones. And I'll give you an analogy of we're going to put these in a blender, blend it up, and then we're going to scoop out 4 new ones. The 4 new ones are going to be identical. So let's mix them all up. Ultimately, this is all based on math. The mixing of these is mathematically based. Okay, and it's also theory, but the theory matches what we observed with our study of the molecule. We're going to pull out 4 identical orbitals. Okay, now these have a certain energy. Usually you graph these with energy. I could have put these a little wider. 4 identical ones. What are we going to call these? They're going to be 4 sp3 orbs. It's called an sp3 orbit, which means it came from mixing an s and 3 p's. But we get 4 of them because this is always consistent. If you put 4 in the blender, you're going to pull 4 out. But they've been blended up now. Now they're all the same. Same in terms of energy. Okay? But also, I could have put this a little bit better. Where does the energy of these fall compared to these original ones?
In the middle.
In the middle, but not exactly in the middle. Why closer to P? Because more P went into the blender. It's like if you put 3 scoops of chocolate and 1 scoop of vanilla, your blend is going to be more like chocolate. Those look more like P's. They have energy closer to P's. Okay, so they sort of fall closer to P in here. Now we got there, and 4 valence electrons in arrows. We can show them here. There are your 4 valence electrons. Now we're ready to make 4 identical bonds. Hydrogen comes in with its electron, and we make a bond using that orbital. We'll talk more about it. We do that 4 times, and you make 4 identical bonds to hydrogen. using these hybridized orbitals. 4 sp3 hybrid orbitals. What do those orbitals look like? Well, this can be difficult to show because I'm not a good drawer. We might pull up conjecture there. Shown in the back a little bit. Before we show them, let's kind of look at how they're combined a little bit. I'm not going to show this combining with all three because that gets complex. I'm going to show just an S combining with a P and what that may look like. Okay, an S is spherical, right? Nucleus in the middle. If we sort of put a P on top of it, first off, that has some type of phase, and we'll call it maybe positive. If we put a P there also, it's going to look like this, and this has, the lobes have opposite phase. And these orbitals are waves, and when waves come together, they can come together and make a bigger wave, or they can come together and actually cancel each other out. Okay? Like in the ocean, waves can actually cancel each other out, or in a lake. Also, sound waves, you can't have sound being canceled out. Over here, where the phases are the same, they build. But over here, this portion where this is the S is positive and the phase of that is the opposite, these cancel out. And so you end up with nucleus here. On this side, we get sort of enhanced. Okay, this is not to scale or whatever, but it's showing kind of this enhancing. But over here, this sort of gets canceled out. And you end up with, now since we combined an S and a P, what do you want to call this guy? And what? It's an SP orbital. Just one, but we call it that because we're not creative enough to call it anything else. Okay? You understand though? Now, I'm not going to try to do it by combining 3 P's, okay? I can't do it. It's too complicated. All right. Well, let's go back over here. We got 4 of them. Here's the carbon. How are these 4 oriented around the carbon?
3 different axes.
Well, it goes back to what you should know from Gen Chem. We have 4 electron regions here. How do you orient 4 electron regions with the most space? Give that
109.
Tetrahedral, right? Tetrahedral. Now tetrahedral, I'm going to draw it out the orbitals first. Tetrahedral is always 2 in the plane, like this. 1 forward, and when we draw forward, bolded, okay? And 1 back. And the back, sort of like this. Now, could be done better. Really, this one is right behind this one. But usually I just draw it like that. Tetrahedral, yeah? Plane, 1 forward, 1 back. What do we have here? They're the 2 in the plane. 1 straight up in the board. Okay. The board was just moved out right through here. That's on the board, and that one is drawn on the board. But then this one is not drawn on the board here. It's coming towards you. It's kind of this. Then the other one here is going back. And like I said, the one that's going back is sort of right behind the one going forward if you look at it. But on my view, I sort of drew it a little bit up. Okay. But that's it. And the bond angles here are what? All of them. Now the easiest one to denote here would be this one in the plane, but this is 109.5, right? But also here and here, all these bond angles are 109.5. Why? Because that's the maximum way you can spread all these electrons out. Back over here, this was 90 if it was all planar. Well, the bigger bond angle is more spreading out. We're using 3D here as opposed to a flat like this. This is not even the right geometry here. But what do the orbitals look like? Okay, well the orbitals are there. Those are actually orbitals. Actually, let's draw them in here. Okay? That is the orbital. Now, it's going to look kind of like a P. But remember, it's hybrid. Okay? I only drew one side. If I just drew half, you might say, well, that's half of a P if I did the other one over here. Well, guess what? The one over here is really not that big. It's real small. So really, on the opposite side of the atom, coming through here, that back lobe is there. Okay? The nucleus there, the back lobe. And that's what this is usually called, the back lobe over there. And we usually just don't even draw it because it just makes life complicated. We just sort of draw half of the hybrid, the business end. Okay? Now, we'll never talk about the back lobe, but when we get over to the end of the course, we'll talk about backside attack. And that's where the back lobe sort of comes in. It's there. But all these are here, okay? Might be best to keep that in. Oriented tetrahedrally around the carbon. There are your 4 hybrids. Okay? Now, what are they interacting with in methane? Making a bond to H. What type of orbital is the H using? The only one it's got, an S. And it's not hybridized, it's the 1s. And the shape of the 1s? Spherical. Okay? So here's that. Spherical. Okay? And this is the H. Okay, and guess what? The H, the carbon supplies an electron, and we drew those as arrows. And the H supplies its 1 electron. I'll draw that as X. And what am I trying to illustrate here?
Covalent bond.
A covalent bond, which is what? Overlap of 2 orbitals. What orbitals? It's the 1s from the H, and what is this?
The SP.
And sp3 from the carbon, of course. Overlapping, doing its magical thing to lead to a bond, because a bond is an overlap of 2 orbitals. But then the book becomes that thick of what all is really going on there. Okay? But what you need to know is what type of orbitals are overlapping to make the bond. And all this instead is denoted, we can come back and just denote it like this. Right? When you look at that, what is all involved here? Question?
So like if you asked us what kind of bond it was, would you call it like an S, sp3, or?
Orbitals overlapping would be sp3 and 1s. If you want to put the shell here, it would be the 2. That gets a little complicated, but we're dealing with the 2 shell, right? Usually you don't call them 2 sp3s, it's just too many numbers and you get a little bit confused. But that is the 1s. It's an s orbital and an sp3. If you don't want to draw the 1, fine. That's what's interacting. Type of bond, though, we need to mention that. This is head-to-head overlap of orbitals. Okay, so this is a sigma bond. Okay, a sigma bond. Did y'all talk about types of bonds, like sigma bonds in Gen Chem? Sigma bond is head-to-head overlap. Like this. Let's get 2 pencils and bond them together. If I wanted to bond these together by a sigma bond, it would be like this, head-to-head. There, they're bonded together. The one thing about that is they can rotate. They can be still stuck together, but I can rotate. Yes, you can. Just like this. Head to head can rotate. But you don't break the bond when you rotate. It's still, the head is still there. Okay? In a minute, we'll talk about pi bond, which is not head to head, but what?
Side to side.
Side to side, or whatever you want to call it. Side to side. And the whole side has to be there. Because of that, you can't rotate. Because if you rotate, you'll break it. It's not just there. So pi bond is going to limit the rotation. So we have bond angles 109.5. We've drawn that before. Ultimately, the bond angle in the hybridization comes from regions because we have 4 electron regions around the carbon. And the regions dictate how many hybrids you need. We'll repeat this multiple times. One thing here before we erase is, we put everything in the blender. Everything was hybridized. Okay? Let's look at another example. Okay, ground state, yeah, we have just our starting point. I don't really need to redraw this. What was this? 2S, 2P, ground state. Let's look at a different compound. Ethene. Slang name ethylene. C2H4. Okay? The only way to put together a structure for that, I believe, is going to be this. I don't know if there's a constitutional isomer. C2H4. 1 DUS. What functional group is this? Alkene. Alkene. That's why it's called ethene. Eth being 2 carbon. Ethene. Or ethylene for slang. Okay? Each of these carbons are going to be sp2 hybridized. They're identical. We'll talk about one. The other one's the same exact thing. Okay. Let's approach this a little bit differently by asking this question. How many electron regions around this carbon? 3, yes. Single bond, double bond. That's one region. 3 electron regions. That's going to equal what? Because that's going to match your number of hybrids. It's going to be sp2. Because we need 3 hybrids. How do you get 3 hybrids? You mix an S and how many P's?
2.
S. We're just going to mix an S and 2 P's. Okay? And that's going to give how many hybrids are we making here?
3.
3. Because you put 3 in the blender, you're going to get 3 out. That has to be consistent. We make 3. What do we want to call these?
sp2 hybridized.
Yeah. Because, again, that's what went in. We put an S in, 2 P's. Now we have 3 sp2 hybrids.
So did we just ignore the other 2s electron?
No, it goes up to,
Other 2, you mean 2P.
it's going to be your double bond.
Like on the ground state of carbon, there's 2 2s electron. There should be another 2s electron there.
Oh, sorry. Like that?
Yeah.
Really, the electrons aren't important. You know, really, we're just showing the orbitals. We'll put in those 4 valence electrons once we get over here. The thing, though, is I thought you were saying do we ignore this? This guy didn't go in the blender. This p orbital is still there. Okay, you can draw it somewhere up here. Same energy, it's still there. Okay, that's the p orbital. It did not go in the blender. It was not mixed. So here's our hybridization here. And the valence electrons of carbon sit like this. Now you might say, well, why did we go up here and we didn't fill here first? We might get to that. 3 electron regions are spread out what way best? Not tetrahedral, but
Trigonal planar.
trigonal planar. Okay? Your 3 hybrids are spread out trigonal planar. Your hybrids set your geometry. Okay? Let's see if we can draw this. Here's a carbon. Now all my hybrids are going to look the same. When we get through, we'll look at relative difference. On the board, they're all going to look the same. 3 hybrids. Let's draw one. Draw one this way. Okay, there's the back lobe. All right, but again, I'm not going to draw a back lobe. Let's see, trigonal planar. Does everybody agree that I did 3 lines there are trigonal planar? Yes, planar and the plane of the board. Nothing's going forward or back. It's all in the plane of the board. Trigonal planar. And so your hybrids are like this. All right, back lobe missing, back lobe missing. So that's an sp2, that's an sp2, that's an sp2. What are these 2 interacting with?
1s orbitals.
The H, yeah. I'm not going to repeat all this, that was done the same as before. 1 electron from H, 1 electron here. There's one of the hybrid bonds. There's the second one. What's the 3rd hybrid bond to? Another carbon. See that other carbon is sitting over here, the same exact thing. Trigonal planar. There's your trigonal planar for that hybridization. Here's an orbital. Here's an orbital. There are your 3 hybrids in the trigonal planar arrangement. Here's the H. Here's the H. Yep, it's the same thing over there. Let's focus in on just one carbon, though. What type of bonds did I just make? Sigma or pi?
Sigma.
3 sigma bonds. 2 of them to hydrogens. Overlap of an sp2 with an s. What do we have here? It's a sigma bond, but it's what? A double? It's not a double, it's just a sigma bond. 1 bond. But it's overlap of sp2 and sp2. Because we got another carbon, not an H. Okay, sigma bond. What's left over on the carbon? P orbital. How do we draw it?
Pi bond, so it's the...
How's it going to be oriented to this? If this is all on the plane of the board, P orbital is going to be coming out. It's orthogonal or perpendicular to that plane. Now, it's hard for me to do that. So I'm just going to draw it like this. What's the shape of the P orbital compared to a hybrid? Relative shape. P orbital would be a little thinner because it doesn't have that S character. Also, a little maybe longer. When you start bringing in S, it makes it more rounded and a little shorter, actually. I'm going to actually draw the P like a little bit longer, maybe, okay? And there's no back lobe that's been reduced. It's full, both sides. But guess what? This carbon over here is the same exact thing. So we can also draw its leftover P orbital. Now, if those are in the plane of the board, the trigonal planar would be like this. And the P orbital would be coming up and down. Or I can say the trigonal planar is in the board and this has to be coming out, like that. Okay. If you look in the book, there'll be some more better 3D oriented views. But guess what? This carbon has 1 electron there, yeah? Okay? And guess what? This carbon also has one electron there, but we can draw it as maybe an X, different. But guess what? These two orbitals, each with one electron, interact. Not only there, but here. How do they interact? That's not head-to-head, but side to side. And what type of bond is that? There's your pi bond, and then your sigma bond. And sigma bond is the head-to-head of your hybrids. Hybrids make sigma bonds head-to-head. Now, it looks like these p orbitals are too far away to interact. Well, that's just because we drew it. In real life, it's close enough to get some interaction. Which bond is stronger, the sigma or the pi? Sigma's stronger. The pi, even though it's all that side to side, I don't notice it overlaps as well. But yes, pi bonds are weaker. So ultimately, what do we have between the two carbons? Two bonds. It's called a double bond. But when you see a double bond, you see one sigma and one pi. That's not too bad of a drawing, yeah? All right.
So when we do the hybridization for sp2 orbitals, why does one of the two s electrons jump up to the p orbital? Like, because we start with two p's and two s's, and then we end with 3 in the sp2 orbital and 1 in the p.
As opposed to,
like S2.
what is that, off-ball, polyexclusive Hund's rule? One of that put here?
No, because like instead of saying like the bottom two and then one of the p orbitals stays down and one of the p stays up, so instead of saying we had an S2p hybridization, like, and because both of the p's come down and one of the s's go up to the top. I guess.
Let's start over here. Let's start with what we know. I mean, we know it's trigonal planar. I mean, you can tell like from X-ray. There's also math here. I'm not quite sure what your question is, but part of your question is we just know it's not because we know what the molecule looks like, and so we're trying to develop a theory to match the observation.
Okay.
Keep that in mind. But also ask me again because I'm not quite sure exactly what the question is.
I'll try to think
I
about
thought you were here because Hund's rule, whatever, tells us we put an electron here. But if you put an electron there,
it doesn't make sense.
it doesn't make sense because it looks like a lone pair. And we know that that doesn't have a lone pair from our observation because science is that we observe things and then we try to explain with some theory. There is no lone pair. So, like I said, you may wonder why is it up here. It's up there because it fits the observation, but there's a little bit more to it if we have a better question and I can't quite
Well,
put my finger on.
I'll try to think about it differently now. I'll ask that.
Okay, now let's look at next compound. What else was there to say there? This, since these two carbons are pi bonded, it's a pi bond between the two carbons. What's that going to do about the rotation between the two carbons?
It's going to limit the rotation.
It's going to restrict the rotation. Now, I don't have good models. I don't know why they don't make good models for sp2 and sp3. This is not bad, it's just small. But this is showing what we have here. Let's throw in some p orbitals because they just showing a double bond, but they're not showing how it comes from. You see that? Instead of that being two things, I thought it's just one bond. Okay. The other bond comes from what's left over. First off, you see it's trigonal planar. If I drew it on the board like originally, you see, boom, boom, boom. What's a bond angle here? We didn't mention that, did we?
120.
All these bond angles are 120. That's standard trigonal planar. 120. It's bigger than 109.5. 120. Okay? But then, there's the plane. P orbitals are perpendicular to the plane. And so each carbon has one, and there's one electron in each, and those one electron in each, those are interacting to make one bond, because one bond comes from an interaction of two orbitals, right? Now, if you want to draw the p orbital straight up, you turn your trigonal planar that way, and now the p orbital is straight up there. That's what you have. But because these are pi bonded, I can't rotate this carbon and spin it like this, because if I did, boom, I'd break the pi bond. The pi bond is not going to want to be broken that easily. It's strong enough to restrict rotation, and so you can't just spin this. Thus, these guys, if they were opposite, I can't spin it around and make them same side. It's fixed. That's what pi bond does. Okay, C. Ethine. Ine. It means alkyne. This is your carbon-carbon triple bond. C2H2. And I think the only way you would get a good Lewis structure would be to draw like that. That's your simplest alkyne. Alkyne, in terms of drugs, one that comes to mind for drugs is most of your birth control pills contain an alkyne functional group. But there's others. We'll cover these functional groups in more detail along the way. Okay, let's see. How many electron regions around this carbon? 2 electron regions, right? Single bond region, triple bond region. And that carbon's the same. So, since we have 2 regions, how many hybrids do we need?
1 or SP, so.
2. Okay, hybrids set in your geometry, it's all interrelated there. You need 2 hybrids. So if we go back to ground state, yeah, you don't really need to keep drawing this if you don't want. What do we have? 2s, 2p, forget about the electrons, just orbitals. We want 2, so we're going to mix one of these and only one of the p's. And we're going to hybridize, and we're going to end up with how many hybrids?
2.
2. What do you want to call them?
SP hybrids.
Just SP hybrids. But we have 2 of them. And we need to talk about the relative shape. We'll start talking about this. You think these hybrids are going to be shorter or longer than an SP2?
Shorter.
They're in between S and P, but are they going to be shorter or longer? Somebody said, why shorter? Yes. Because of this. Keep in mind this. This is 50% S. 50% S. And SP2, what percent S was this?
33%.
Okay. That has more S character. More S is going to be more what? It's going to be more rounded and shorter. Okay? It's simple like that. Or you can go the other way. The more P character, the more longer and skinnier the type is going to be. But you often talk about percent S character. And that helps you understand the relative shape. Because every time I draw them, I can't take time to differentiate. Okay? So we got that. But what's left over? We didn't do anything. You can draw these wherever you want. I mean, something like this. These are the P's that were left over. Okay? And actually, the electrons are going to sit right here. Because in none of these examples does carbon have a lone pair. Okay? I hate to erase that. That's one of the best of all time.
You should have it on video.
We got it on video. Yeah. Okay, we have a carbon. I have 2 hybrids. They're going to be oriented in what type of geometry?
Linear.
Linear. And so we have one this way back lobe but not drawn. We also have one this way, and the back lobe not drawn. And this is an SP, and that's an SP. That's not one p orbital. That's two different orbitals with back lobe of each not drawn. Okay? What's this interacting with? H. That's that story over there. What's this interacting with? We got another carbon with the same exact hybridization. Okay? SP. What is this? Sigma bond between the two carbons. Okay? Because every orbital I'm drawing here has one electron in it. One electron here, overlapping to make a two electrons covalent bond. But what type of orbitals? Okay? And we make a sigma bond, head-to-head overlap there. This is SP, but it's interacting with the H, 1s. What's left over on the carbon? Not one p orbital, but two. Now, one of them we can draw here. The other guy is the exact same thing. One electron, okay? The other carbon also has an electron, but they come together, and that's that. There's one pi bond. Well, what else is on this carbon? Another p orbital. Now, all of that is in the plane, because when you have two p orbitals, they can't both be perpendicular to the plane. All that's in the plane of the board. The second p orbital is now coming out like this, halfway this way and halfway behind. So if I could make this stick here and make this stick here, and then these are interacting this way for a second pi bond. Now, I can't really draw that well. Usually in the books, you'll see it drawn. They'll just be kind of drawn there. And then you'll see maybe a different color or something, and it's showing those interacting. But the two that are like that are really, okay, again, coming straight out. You're interacting with the sides of this. Two pi bonds and one sigma for a total of 3, and that's your triple bond that we just denote with the three lines. So, two pi bonds. Now when we did DUS, we ultimately said that every pi bond is a DUS. So you look at this, how many pi bonds do you see?
2.
2. It's 2 DUS. Okay? And we already said the bond angle, this bond angle here is what?
180.
180 degrees, and it's ultimately linear. So this H is coming out linear compared to this. Actually, the whole 4 are linear because this continues on linear. In the back of the functional groups handout, DUS, there's some drawings. This is just what I drew here. Maybe a colored view in a textbook would be even more better representation. It may show things with different colors. Okay? But you can look at some of that. That's kind of what we drew there, illustrating some things. Any questions about that page? If so, ask at some point. But really, this is a very important page. First with some very nice drawings of mine here, showing just the hybrids. And you do need to know the relative difference in kind of the shapes. And we just talked about that with the percent S. In sp3, again, back lobe right? The sp3 has 25% S, 75% P. So the more P character is going to be sort of elongated more and a little more narrow. As we start getting more like SP and get more S character, what happens to the hybrid orbital shape? It becomes more like S. It becomes more rounded and shorter. So here's an important question, application of that there. Which orbitals would make the longest bond?
SP3.
This would give a longer bond. Yes, it would. And that orbital down there would give shorter bonds. Because if you have two atoms and the orbitals are real rounded and stubby, they're going to have to come closer together to bond. If their orbitals are real long, well, they don't have to come as close, and they can bond, and the interatomic distance is the bond length can be longer.
Would the shorter bond mean the stronger bond?
Yes, that's also the thing. Shorter is going to be typically stronger. But it's just so much coincidence. That's not really the reason. That's a good, we'll be looking at that below. Why is a shorter bond stronger? It really has to do with the hybridization. Which orbitals are more stable?
Shorter bonds.
Because the more stable the orbitals you use to make your bond, the more stable the bond, and thus the more stronger it's going to be. Which orbitals are more stable?
SP.
Why SP?
It's closer to the nucleus, less nodes.
Well, it's just like, okay, which is more stable, an S or a P?
S.
S.
It's less hybridization too.
Well, it's mainly just S character. S is more stable than P. S, the electrons can be closer to the nucleus, all that. So it should hold that the more S character you have in your hybrid, the more stable the orbital is going to be when it's used. And if the orbitals are more stable, that's going to lead to stronger bonds. So that's ultimately the reason. But yes, you can say shorter is going to be a stronger. But it has to do more with the understanding that it's the S character about it. Okay, down below. More application. Most of this we've kind of already answered, but let's go look at it again. This is from a different textbook other than the Klein book. So, a little bit of review and some numbers here. Let's make sure they make sense. Ethane. We're talking about both carbons are sp3. See, that's not drawn right. That looks like it's 90-degree bond angle. That's not drawn right. They're both tetrahedral. A lot of times in here, things won't be drawn correctly. And it will actually cause you beginning students to be a little bit confused, and I'll have to say, well, they just didn't do it right. And you're like, oh, I thought about that all weekend. Well, sorry. Just be aware of that type of stuff. Both carbons are sp3. Bond angles around those carbons here. Bond length. You don't need to know the exact bond length, but only the comparative, the relative comparison. This is in angstroms. Okay, typical bonds are, about 1 angstrom, 1.5 angstrom. That's the carbon-carbon bond length. Would you expect the carbon-hydrogen bond length to be shorter or longer than that?
Shorter.
Why shorter?
Hydrogen
That's S.
Because you're using the s orbital, but it's not even a 2s, it's a 1s. That's a smaller orbital. Okay? Strength of the carbon-carbon bond. They're giving it both in kcal and kilojoule. I usually quote kcal. Here's the length of the CH bond, shorter, yeah. And what else is up there? Strength of the CH bond. Let's move that a little bit.
Stronger.
Okay, let's look at the next one here. Both carbons are sp2. Geometry or bond angles around the carbon. Trigonal planar, 120 means the same thing. Trigonal planar. The trigonal planar is important because all the HH in carbon is all on the board. There's nothing forward or back here. Same as that carbon over there. Trigonal planar. Length, okay? Carbon-carbon bond is shorter. And I should say the carbon-carbon interatomic distance, because we're not really focusing on one bond. The distance between the carbons is shorter. Why?
And it's double bonded. They'll hold tighter together because the bond lengths are short.
Well,
SP2.
need to go back to the hybridization.
Right.
The hybrids said everything, give you the answer to everything. What type of, this is a sigma bond here, right? The sigma bond is made up of overlap of what?
SP2 orbitals.
sp2, sp2. But this sigma bond here is what?
SP3.
sp3 to sp3. That's why you have shorter and longer. Well, what do you know about the size of these orbitals here? Shorter orbitals. We're going to make a shorter bond. The hybrid set your bond length and your geometry, everything. So it has to do with the orbitals that are used. Shorter orbitals make shorter bonds. Come down here, even shorter distance, because here you have what? sp, sp with a sigma. And then you have 2 pi bonds thrown on extra. Okay? Then the strength. We have to be careful here. I don't like their heading. They're talking about the entire bonding between the carbons, not just one bond. You may think, are they just talking about the sigma bond? No, they're talking about the entire thing. First off, this is a double bond, so you would expect it to be stronger than a single. But it's not doubly strong. It's not 180. Why not 180? Because a double is not just
You get the pi
Two.
bonds.
It's not two sigma bonds.
no. It's a sigma and a
Pi.
pi, and the pi is weaker. So the pi does make it stronger total, but it's not like doubly strong. And then why is this not 270? Well, because it's only 1 sigma and then 2 pi. You're bringing in the weaker pi bonds. Okay? But a triple bond is typically stronger than a double if you're talking about the same carbon. So know the trends, know the understanding that the percent S character really answers a lot in terms of bond strength and bond length. Then we can start looking and asking questions about molecules. What's the question here? Rank bonds A through C in order from longest to shortest. Which bond is longer? All these are carbon-carbon bonds. Which one's longer? What's the hybridization of this carbon? Okay, we need to get used to line bond formulas. How many H's on this carbon? 2, right? Carbon makes 4 bonds. There's 2 drawn, undrawn H's. How many H's on this carbon?
1.
1. How many H's here?
None.
None. Here?
1.
1. Okay, all bonds are here. What's the hybridization of this carbon?
SP3.
sp3. How do you know that?
Because there's 4 bonds.
4 regions,
Four
sp3.
regions.
And that guy there?
SP3.
sp3. So, bond A is made by overlap of what type of orbital?
S-
2 sp3 orbitals. That's it, because these carbons don't have p orbitals. So this is sp3, sp3. What's hybridization of this carbon? sp2. How do you know it's sp2?
3.
3 regions is sp2, until we tell you an exception. Since it's sp2, it has how many sp2 hybrids? 3, and they're in what type of arrangement? Trigonoplanar, which is like this. You see how that has, you see your trigonoplanar? But what else does this carbon have that was not hybridized? P orbital, it's there. But guess what? This other guy also has a p orbital that wasn't hybridized. And there's your pi bond that's drawn in there. Okay, but it's sp2. So, bond B is overlap of what?
SP2.
sp3, sp2. So it's shorter because we're using a shorter orbital. Okay? How about this guy?
two sp2.
Well, this carbon's also sp2. So carbon C is made from this. So rank those from longest to shortest. Longest will be which one?
sp3, sp3.
Longest, then what? Longest to shortest. Longest to shortest. Types of orbitals used. All these are single bonds, so they're sigma bonds. Sigma bonds are made with hybrids. What's the hybridization of the nitrogen?
1, 2, it's got a long pair of those, so
Hybridization of the nitrogen. It's the same questions we asked before. Just because it's an N, it'll make a hill of beans difference. It's the electrons that are there.
SP3.
How many electron regions? Well, it has a lone
4.
pair.
So it's got 4 regions.
4 electron regions. sp3.
Trigonal.
Okay, graph that hybridization. We graphed each of the 3 when we did sp. I've already erased it. I started with ground state, but we ended up with the hybridized state, and that's what I'm saying in the graph. If you agree it's sp3, then that's a starting point. sp3 is going to have how many hybrids?
4.
4. Any p orbitals left over?
No.
No. Okay. How many valence electrons does nitrogen have? 5. So we're going to have 5 arrows over there. Okay. Here's the way I recommend doing it. First off, I'm the only one that I know of that asks you to graph hybridization. I don't understand why. Because it helps explain it, and it's like doing math but never telling you to use a formula. I don't understand. That's it. Okay. But let's look at this. What type of bonds do you see this nitrogen making? Single bonds are always sigma bonds.
So 3 sigmas.
3 sigma, 2 of them being to carbon. Okay. Well, right here. Sigma bond to carbon, sigma bond to carbon, sigma bond to hydrogen. Okay. That is, here's the electron from nitrogen interacting with 1 electron from the carbon. Okay. Same thing here. 1 electron from the 8. What else do you see on the nitrogen?
Lone pair.
Well, where in the heck do you want to put that? There's your lone pair. Okay, it's sitting in a, what type of orbit?
SP3.
The lone pair is in what type of orbital?
SP3.
Yeah. There it is. Now, if you drew the nitrogen, what's the geometry of all those 4 orbitals around the nitrogen? Tetrahedral. Let's draw like this. 2 in the plane, 1 forward, 1 back, yeah?
Yep.
Okay. This one up here, these are orbitals. Okay, do I have to draw in and make them look like an orbital? It's an orbital. Yes, let's do that. There's your 4 hybrids. This one's interacting with an H, right? This one's interacting with what? You got another carbon down here, and it has a certain hybridization. But let's just, and then you have over here, either way, it doesn't matter, I'll do it here. Then you have another carbon over here, and it has a certain hybridization that you can consider. But lo and behold, what's in this orbital? A lone pair. But it has a certain orientation. It's just not interacting with anything. And all that's spread out in tetrahedral. Okay, let's look at hybridization of the oxygen. Think about that. We'll take a 2-minute break. Hybridization of the oxygen. Anything, any of them, anyone that want to do. Fluorine. Think about the oxygen. 2-minute break.
Actually, I have a question. When we were doing degree warm-up, she had the, I'm going to look back, she was and wanted to carbon and hydrogen. She said that like there was in the people, not the SPP models for that
Does a neighboring atom have a p orbital? A neighboring atom has a p orbital, the lone pairs don't want to be in a p orbital.
Okay, so that's fine.
So it's an exception.
Are we gonna go over that?
Yeah, this oxygen would be an exception.
Okay.
Because it's, like here, we drew this lone pair. Is that lone pair interacting with anything? No. That's not the best case. If we can have one of the lone pairs interacting with something, that makes the bonding better. And we can do that, the molecule can do that, if there's a p orbital next door. And this is something you have not heard before, but it's very common to organic chemistry, and it's the foundation of, one of the foundations of resonance and conjugation stuff. We'll see it with this oxygen. I wish we had a nitrogen that did this, because the oxygen has 2 lone pairs, and so but still, we'll do it with this oxygen. Okay, everybody back? Sounds like it? Okay, 2 lone pairs here, right? What's the hybridization of the oxygen?
SP3.
First off, before any exception, you say sp3, right? Why? 4 regions. Lone pair region, lone pair region, bond region, bond region. 4 is sp3. Yes, unless there's an exception. This is going to be an exception. First off, it was sp3. Let's just quickly do it. It's going to be wrong. We would say what? Boom, 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 sp3. What type of bonds do you see the oxygen making?
2 sigma.
1 to carbon, and the 2 lone pairs are sitting where? sitting here. All this is spread out tetrahedral, okay? Except two of the areas are just lone pair occupied. It's not like this. You'd like for these to interact with something, and indeed it can. If there's a p orbital next door, one of the lone pairs is going to want to be in a p orbital. Is there a p orbital next door? Yes, left or right?
Right.
That carbon over there is sp2 with a p orbital. Okay? The p orbital next door. What we're going to do here is we're going to put one of these lone pairs in a p orbital so it can interact with the next door p orbital. Even though that is interacting like that. Just because one p orbital is interacting over here doesn't mean it can't also interact on the other side. And that's called conjugation. Conjugated. Okay? See, if we didn't put this in a p orbital, we would say, well, this is not going on, and we would just stick these out here like that, tetrahedrally. But it's better, it's lower in energy, it's better bonding if we can do that. So that's sort of the starting point. Now, since we're going to say we want it to have a p orbital, but if we want to have a p orbital, it can't be sp3. sp3 don't have a p orbital. So instead, we're going to say it's sp2. And we're going to have 3 hybrids and a p. Now let's get rid of this. Now we can still ask the same questions. What type of bonds do you see this oxygen make? What type of bond is this to carbon?
Sigma.
Single bond, which is a sigma bond. I see a single bond to carbon, sigma bond to carbon, and a sigma bond to carbon. What else do you see? 2 lone pairs. But one of them is in a p orbital. Why? We explain why. Because if we put it in a p orbital, it can interact with the next door one. Where's the other lone pair? Well, the other lone pair is in a hybrid. And if you draw this oxygen here, trigonal planar, let's see if we can do it trigonal planar. Boom, boom, boom. These are your hybrids. Okay? And this is the carbon. That's the carbon orbital. And that's a lone pair. There's your trigonal planar. But then this also has a p orbital. And that p orbital also contains a lone pair. And we can draw that however you want. Why? Because the adjacent carbon has a p orbital. And the lone pair, this can start interacting. So the take-home message is this. Anytime a lone pair is next to a p orbital, in the example you just asked about, we're going to have the exception. It's going to want to move into a p orbital. The geometry thus changes from tetrahedral to trigonal planar, and it goes to sp2, and that's a better bonding arrangement. How do we know it's trigonal planar? Well, you can do X-ray crystallography and you can actually see bonding. And if you did X-ray of this, you'll see that this is 120 rather than 109.5. And that could be the starting point. You would say, well, how the heck is it 120? And then you can go back to what I just explained and say, well, maybe that's what's going on. And ultimately, that's your prevailing theory. Question?
So the reason that the P is not a bond is because there's not 2 electrons or 3.
Is it? Are you saying is this not a bond?
I mean, I know that's not a pi bond, or there would be a double bond, but
That's where we get into delocalized bonding. When you look at this structure, you got to kind of see that there's some bonding in here. Because we have resonance and conjugation. And once we have that going on in the molecule, the given structure is not absolutely correct.
so,
There's some fuzziness here.
so even if there was 2, it still may not be a bond. Like if there was 1 in each p orbital. You know how when we did the last structure, there was 1 electron in each p orbital, so it formed a pi bond?
Yeah,
In
well,
this
you don't
case,
have a
it's
formal
right.
pi bond here. You only have sort of resonance.
So-
Let's
So-
look at another one.
So it's kind of halfway between a single and a double bond.
Yeah, in fact, we'll call it hybrid. It's a blend. There's some pi bonding there.
kind of bouncing.
There's some unseen pi bonding here that a student needs to know about. And that's resonance conjugation. Let's do another example. Where's the green sheet? I don't even know where I'm at.
Dr. Stevens, real quick before we move on, is that trigonal planar or is it bent?
Okay, I know in Gen Chem you learn things like bent. I never ignore the lone pairs. I'll never call it bent.
Okay.
I always give electron geometry because I don't understand how you can ignore electrons. Okay, key exception there, yeah. We just went over that. Drug examples in the syllabus. We can look at another example. Maybe let's look at another oxygen. Syllabus, drug page, another oxygen since we did that. And we can do okay, Lipitor. It's oxygen here. Hybridization. It's hybridization of oxygen. Well, there is 2 lone pairs there, right? How many electron regions?
3.
And this is where we're going to have to clarify the exception when it does not have 3. So the hybridization is what?
SP2.
SP2. Yes. Now you might say, hey, there's a p orbital next door. So carbon doesn't have a p orbital. Well, let me say this. First off, you're never going to ever go to what looks like sp2. You're never then going to go to sp. It'd be very rare. You can theoretically do that. The exception only occurs usually when it looks like it's sp3, but it's actually sp2. I'll maybe explain why. But that's sp2. But since I told you that, now graph it. And tell me, like, for example, what type of orbitals are the lone pairs in? Okay, sp2 has this setup, right? 3 hybrids and 1 p. Okay, what type of bonds do you see the oxygen making?
Pi and a sigma, so
It's making 2 bonds to 1 carbon. What type of bonds is it making? It's making sigma bond to carbon, and what else? Okay, what do you use to make the pi bond?
p orbital.
Yes. Okay? There's your double bond. So, where are the lone pairs?
The sp2 orbital.
They're right there. Both of the lone pairs are in their hybrids. And if you drew that oxygen, here's the carbon, here's the oxygen. There's your trigonal planar. This is a lone pair. Now sometimes instead of drawing the orbital, sometimes you'll see books do it like this. But that's a hybrid orbital with a lone pair. Okay? There's your trigonal planar. Those are hybrids that your geometry, hybrids. Okay? Well, what's left over on the oxygen? P orbital. It's here. It has 1 valence electron, but guess what? The carbon also does too. So I'm just going to have to draw that. These are really coming out at you, but I'm going to have to just draw it like this. That carbon has 2, 1 electron, and this is making the pi bond. So between the oxygen is a sigma and a pi. Now here, this is why some students say, well, I thought you said if a lone pair is next to a p orbital, it's going to want to be in a p orbital. But it couldn't, because if you put this in a p orbital, it wouldn't interact with this one. It would have to be orthogonal to this one, because this one is already there. You can't have both of these interacting with this. So this is where it doesn't take place. You're not going to go from sp2 to sp.
But there's already a p orbital.
If there's already a p orbital, you're not going to do it. The only way you would do it, and I'm getting a little bit past where I want to go, if this had another one, then that could be there. If you had another one that was available, then you can move that.
So you can only have as many p orbitals as the atom you're next to.
Perhaps that's the answer. I'd have to hear you say it again. The exception only occurs when it looks like it's sp3 coming out of gentium, but it's really sp2.
So since there's a double bond and that pi bond is present, then it won't change its hybridization.
You're all making these statements. I'm going to have to really think about it before I can say yes, that's right. Let's do more examples and see. Okay. Let's do a nitrogen. How about the same nitrogen? Graph the hybridization. And then we need to move on. On that page 2 of the workbook, there's plenty of these to be doing. Okay, including DUS, formula, bond angles, all types of stuff on that page. Hybridization of this nitrogen. First off, how many regions?
4.
4. But is anything going on? It's got a lone pair. Is there a p orbital next door? Yeah. It's actually sp2. And what we have here is sp2, p orbital. What type of bonds do you see the nitrogen making?
Sigma
Sigma bond to carbon, carbon, and to hydrogen.
and a lone pair.
And a lone pair, okay, LP and p orbital. Very important to know that. That's the foundation of a lot of resonance and conjugation. Why is it in a p orbital? So it can interact with the next door p orbital. There's actually next door p orbitals on both sides. Nothing else on this nitrogen is interacting with those p orbitals, so the lone pair is like, ooh, I want to move in and interact. Yeah, I like this. More stable. So it adopts a different geometry than you would traditionally expect.
The lone pair is in the p orbital because there's a pi or a.
Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Except if the p orbital is already being used or something. You need to start doing some problems. And we'll see what type of questions we have tomorrow about this. Okay, page 2 in the workbook, lots of these to be doing. Okay, other hybridization examples. We skipped a couple of important ones. CH3. CH3. This doesn't seem quite right. H. What else is here? Could be a lone pair because you don't show lone pairs in formulas. What if it was just this? What's the charge of the carbon? If that's all we know.
+1.
Positive charge. Okay, gotta know how to determine charge. Carbon can be positive. We'll actually see it a lot. It's called a carbocation. That's short for carbon cation. It's called a carbocation, very common. What's the hybridization of the carbon? What's the geometry, bond angles there?
SP2.
Here we go. Charge has nothing to do with this. Forget about the charge. The fact that it's a carbon has nothing to do with this. It's all about the electrons there. How many regions are there?
3.
3. 3 electron regions equals what?
SP2.
sp2. Okay, sp2 looks like what? Boom, boom, boom. P orbital left over. What type of bonds do you see carbon making?
Sigma bonds with hydrogen.
Sigma bond to hydrogen and sigma bond to hydrogen. There you go. What's in the p orbital? No, I didn't draw a lone pair. If I had drawn a lone pair, it would have been a positive charge. So we didn't go that way. There's nothing. Empty p orbital. This is a hybridization thing you should know here. Empty p orbital. Does this carbon have an octet?
No.
Oh, 2, 4, 6. You also see it here, 2, 4, 6 in terms of the shared. You get to count the hydrogen atom too. Okay? An empty p orbital. Do you think this molecule here would like to have some electrons?
Yes.
Do you think it would like electrons? Yes. And if you like electrons, what would you call it? Oh, okay. That sounds like it likes nucleus. If you like wine, you can be called a winophile. If you like money, well, I don't know, but if you like electrons, you'd be called an electrophile. Okay? Or you can be called electrophilic. It's going to like electrons. So in terms of reactivity, this is sort of a starting discussion for reactivity. Some electrons are nearby. How could some electrons be nearby? I don't know. Maybe if you had ammonia with a lone pair, maybe the electrons would be attracted to this. Not only because it's a plus, but because it needs electrons. Okay? All right. No more about that. But empty p orbital, very important to know there. Carbocations, we'll see lots of those down the road. What if we stick a lone pair on there? Let's call it a lone pair. This is also possible. Not as common as the cation. Carbon tends to be more likely cation, but this is also. What's the charge of this guy?
-1.
Negative. 1, 2, 3, 4, 5. What do you want to call this? A carbanion, yes. What's a hybridization of this carbanion? How many electron regions?
4.
4 electron region equals sp3. Any reason for this to want to be in a p orbital? Is there a p orbital next door?
Not right
No. I mean, H doesn't have a p orbital. So there's no exception here. sp3. What type of bonds do you see this making?
Sigma to hydrogen.
Here could have been the starting question. The lone pair is in what type of orbital? sp3. That's the only type of orbitals it has. Sigma bond to hydrogen, sigma bond to hydrogen, sigma bond to hydrogen, and lone pair. I think graphing is useful to help answer your questions and be organized. Making sense? Do some more problems in the workbook, see what type of questions come up. We'll see lots of carbocations down the way. Occasionally we'll see carbanions. These do not have typical bonding. I don't know if I said yesterday, typical bonding. If it doesn't have typical bonding, usually there's going to be a charge. Hey, I don't see 4 bonds of carbon. Probably going to be a charge. Hey, that's not typical bonding. That's not 4 bonds. Probably a charge, and indeed it is. Okay, let's skip the O2. Word about MO. MO theory. Y'all do any MO theory in Gen Chem? No? Remember I took Gen Chem, we spent a lot of time on MO theory. I remember it. Huh?
What was that?
Molecular orbital theory. You know what I'm doing? Yeah? You did a little MO? Okay. Basically what we're doing here is not MO, we're doing valence bond theory. Okay? Molecular orbital theory is where you make molecular orbitals. We're hybridizing, but the orbitals still belong to each atom. We're keeping atomic orbitals, we just have hybridized atomic orbitals. Molecular orbital theory is a more advanced theory where you get rid of atomic orbitals and you have one orbital that's spread over the entire molecule. And it's called a molecular orbital. No. But molecular orbital actually is, there's some people at the high level that don't do any of this. All they want to do is molecular orbital. Because some of this is actually kind of proven a little bit wrong. For example, oxygen. If you do a low structure of oxygen, yeah, 2 bonds, 2 lone pairs, O2, looks like good. Problem is, that doesn't fit the observation. We know that oxygen is paramagnetic. It's got magnetic properties. And to have magnetic properties, you have to have unpaired electrons. Where's the unpaired electrons? I see lone pair, lone pair, lone pair, lone pair, bonding pair, bonding pair. So how could it be paramagnetic? Oh, we have a problem. That's a failure of valence bond theory, and if you do MO there, MO will be more correct. But MO is too advanced. If we try to do MO, it would be like. So we're learning the sort of the most useful, but it has a couple of problems. When we cover aromatics, we'll do more MO theory, because you have to get into MO to understand aromaticity. Okay, I think we're ready for another handout. Polarity of covalent molecules. This is going to be in the physical properties, the white handout, physical properties. There's some warm-up questions there to be thinking about. Okay, polarity. Working our way towards physical properties, molecules, intermolecular forces. Okay, hydrogen. Okay, nonpolar. That is, we know that this bond represents 2 electrons, right? Make a bond. And we say it's the overlap of orbitals. With the 2 electrons sitting in between here, they're sitting there symmetrically. Does one hydrogen nucleus pull them more than the other?
No.
No, they're equal. So it's equally distributed between the 2. That's called a nonpolar bond. On the other hand, HCl is going to look more like something more like this. The electrons that are sitting between are more pulled toward the chlorine. Now, because the electrons are more over here, your entire thing, the electrons are perturbed towards one side. And so that's polarized, because if more electrons are here, if we consider this a whole thing, this would be more of the negative end, because the electrons are more that way, and this would be more of a positive end. That's just sort of physics. Now, we're not talking about formal charge here. This is a partial charge coming from the disturbing the electrons, moving them there. Illustrated like this, Or with a dipole arrow, the electron's moving this way, and sort of on this end, you're trying to show the plus sign. Not formal charges. Now you have other polar bond. The carbonyl is a polar bonding. The oxygen, why is this polar? Ultimately, you can go to the electronegativity. Chlorine's more electronegative, so it pulls the electrons, okay? It's like, hey, we're bonding, but guess what? I'm pulling. I'm greedy, and I pull the electrons. Where the hydrogen would not do that. Oxygen pulls, okay? So we end up with partial plus, partial minus. And the electrons that sit between here, you kind of got to know that they're more towards the oxygen. You get this polar thing here. It's shown here, yeah, carbonyl's polar. So, I mean, you could have some fancy things, odd things here. An interhalogen, ICL. Any difference in electronegativity? Yes, chlorine being higher than iodine, more electronegative, so it cools. Which halogen is more electrophilic?
Chlorine.
The iodine.
Oh.
No, electrophilic means it's going to...
More electrons.
Electrophilic and electronegativity are not the same thing. Electrophilic means it's going to love to have some electrons. It's kind of...
Orbitals are bigger, so it pulls all that stuff in.
No, electrophilic, positive things are going to be more electrophilic.
Because the electron.
Yeah. That is, if I had some electrons, think about it more like this. More like instead of what it wants, what happens. If I had some electrons here, the electrons would be more attracted to which atom? Iodine, because it has a partial positive. These are negative, that's partial positive. And since it's attracted to the iodine, we call the iodine electrophile. The electrons, it's going to like the electrons from that particle. So the iodine is more electrophilic. But at this point, it's more partial positive. How about this guy? Which one's more partial positive?
Bromine.
Well, the same thing, yeah, because bromine is still less electronegative than chlorine, and so you get this. And so if I had some electrons, it would be attracted to the bromine. Chlorine doesn't need electrons, it's already stealing them from the bromine. That type of thing. Okay, water. Okay, here we have multiple individual dipoles. The oxygen, O and H, oxygen is more electronegative. And so here we get partial plus, partial negative. Same thing here, partial plus, partial negative. Okay, so when you have multiple dipoles, you have to kind of sum them up. And in total, is this a polar molecule? So all those are polar. Is this, or do they cancel?
No, they don't.
Do they really?
No.
As it's written, they do, but in real life.
Okay, because that's not a correct structure, right? It's not linear. It's this, right? Let's see. 2 in the plane, 1 forward, 1 back. Lone pair, lone pair. There's your tetrahedral. I mean, are these linear? No, this is 109.5. That's not a correct structure. Okay? So we have this here and this here. Are these dipole arrows canceling? No, they're not. They're equal, but they're not exactly opposite. They are actually creating one big dipole. If the summed up would be through here. You ever do vector summation in physics or math? I think it's kind of like that. Okay? So ultimately we have a net dipole coming from the summation of the individual bond dipoles. The net dipole is called the dipole moment. That can actually be quantified, but we will not be doing any of that. Ultimately, we just call it polar. If it has a dipole moment, molecular dipole moment. You got to know geometry. Because, like, yeah, if you think the geometry is linear, you say, hey, let's cancel. What about over here? What do we have going on over here? Bromine is more electronegative than carbon. Okay? So you have this, so you got some partial plus, partial minus. Now, word here. You never consider any dipole between C and the H. It's very small, but it's so small we just ignore it. And so we basically consider CH bonds as being nonpolar. Okay? So we see that the carbon is going to be a little electrophilic. It would be attracted to the electrons. It would like the electrons down the road. So overall, that's a polar molecule because there's nothing canceling out that individual dipole. Yeah? Okay. We'll do maybe a couple of these, and then I'll let you do the rest on your own. We'll see what type of questions they may be. We've already done water, right? Water. How about CO2? Polar or non-polar?
Non-polar.
Non-polar? Let's see, a loose structure. Most common is to put the carbon in the middle. CO2 that we exhale would be like this. Now what do we got? Lone pair, lone pair, lone pair, lone pair. Does it look like a good structure? Hybridization of the carbon. Linear? That's an interesting carbon because it's kind of like two double bonds. But you should still be able to graph it. It's the same.
SP. So
It's SP. What type of bonds do you see?
sigma.
2 sigmas and 2 pi's. Graph it. It will all fall into place if you know what you're doing.
So the 2 sigmas would be in the sp orbitals, and then the pi bonds would be in the p orbitals, correct?
Okay, but that is a good structure. So it is linear. Dipole here, boom, and boom. But since it's linear, they're equal. They're also opposite, and so they're going to cancel, and it's going to be non-polar. What's consequences of it being non-polar? Why do we care? Not non-reactive. Do what? Solubility, because polar solvents dissolve polar things. CO2 is not. Is CO2 going to have high solubility in water? It may have some because there's other things that could potentially be going on. In physics, we talk about what if I had a positive charge down here in this molecule? Would it cause any torque on the molecule?
Yes.
Like, would it cause the molecule to spin or rotate or anything, some consequence?
Yes.
Well, wouldn't these electrons be attracted to this? So wouldn't this end kind of maybe want to spin down? Why not?
Because the other side's pulling down the equal.
Ah, yeah, because the other side, and so instead of torquing, it just kind of sits there. And the consequence, and we say, well, because it's non-polar. I mean, there's many applications of something like this. But if we change this to S, you think that's polar or not polar? That's polar because yes, they're opposite, but they're not going to be equal. You got to think about molecules. We get used to seeing them on the board like they're these O's and C's, but a molecule is just sort of a package of electrons. Okay, what about SO2? I'll let you do that one on your own and think about it. CCl4. That's let's see. That's a carbon just bonded to 4 chlorines. What are we going to have? Tetrahedral?
Mm-hmm.
Is it okay if I don't draw the lone pairs on chlorine? I mean, I don't want to waste 20 seconds of your time. Chlorine has lone pairs. Yeah, tetrahedral, right? Polar, non-polar.
Non-polar.
I mean, they all have individual dipoles. Are they going to cancel?
Yes.
Yes. Consider this, each one chlorine. One coming straight up is actually going to be canceled by 3 coming down, but only partially down. Okay? And they do cancel. One straight up canceled by the 3 coming straight down. This is better to have maybe models here so you can hold it. Okay, 2 in the plane, 1 forward, 1 back. What's after CCl4? Carbon tetrachloride, what's next? CH, yeah. What if we change one of these to an H? First off, do we even consider the CH? No. We got 3 coming this way. Boom, boom, boom. How do those sum up? Sort of 1 straight down for A, okay? Anything coming to counteract that? Nothing. No, you have a dipole. I know I just kind of erased on the board. You can't do that as easy on the paper. Without getting rid of the first one. But the net dipole here is what?
Towards the chlorine?
See, this is where they're drawing. The net dipole is sort of straight down. Again, you can see it better here. These 3 coming here are going to sum up to 1 straight down. Okay? So understanding the dipole direction there. That's carbon tetrachloride. This is called chloroform. That's a common name. Dichloromethane. I'll redraw it here. If we put another one there, what do we get? The H is here. Do it like this. Polar, non-polar? Yeah, because we have boom and boom. Are these equal opposite?
No.
They're equal, but they're not opposite. So if we make the H's green, you can show this however you want. Let's show them the H's up. 1 dipole, electrons towards the chlorine, but those sum up as what? 1 straight down. Okay? And there's nothing to counteract the 1 straight up. So it's a polar molecule. Here we can sort of show the net dipole kind of between the 2 chlorines. Or if you have them like this, between the 2 chlorines. Yeah? How we doing on time? Time to get. Let's see where we're at. Please do the ones that we didn't do there. SO2, that's the only one we didn't do. Okay, let's do this kind of quickly because I think it's pretty straightforward. The extreme of polar would be ionic. Okay, that's where the electrons the atom just took them. Like maybe an ionized. And then tomorrow we'll pick up with physical properties. Please be looking ahead so everything is not brand new tomorrow. Any questions before we end? See some of you this afternoon. We'll check in. Instructions are in the lab manual for check-in. After check-in at 2:30, we'll come down to this room. Hopefully it's available for lecture. We'll talk a little bit about IR. Okay, guys, have a good day.
this each day, that would be good.